Hi everyone. Today we're going to talk about, we're going to continue to talk, this is in the second half of the class, we're going to continue to talk about a very cool theorem. So previously we talked about the law of large number. That's a very good theorem. And another very important theorem is the central limit theorem. And at this level, I don't expect you to be able to prove it, of course, but I do want you to understand what it is and how to use it. We talked about it before, that the law of large number is that if it says that if you repeat an experiment for enough repetitions, then the whole whatever the sample that you're coming up with will get closer and closer to the whole population characteristics. The most important characteristics we are talking about here is the average or the mean, right? So the central limit theorem is oftentimes kind of got mixed with the law of large number. But the central limit theorem is basically saying that if you change the sample size, then the sample will get closer and closer to a normal distribution. So the two of them is slightly different. I would say fundamentally different. The law of large number is basically saying if you do the experiment enough repetitions, right? So that experiment could be different sample, it could be other things. The central limit theorem is, the law of large numbers say if you do enough repetitions, then the result will not be biased. The result will not be systematically different from the population characteristics. But the central limit theorem basically says if you do it a big enough sample, you can think about that sample as the enough of repetition of picking up the sample, or you can think about a sample as a big random sample. So if you do that enough times, then the mean is going to satisfy, the mean is going to be normally distributed. We're not talking about is it biased or not here. We are specifically talking about a distribution, the probability of having a mean will be distributed according to normal. So namely the mean, the mean of the mean will be centralized as a population mean, and the standard deviation of it is also well defined in that case. So coming back, and let's talk about a little bit more detail in the central limit theorem. So first of all, we can look at the central limit theorem for sample means. So suppose the x variable is a random variable with a distribution that may be known or may be unknown. So that x itself can be uniformly distributed, can be exponentially distributed, it can be any kind of unknown distribution. Then we can say, suppose we denote the mu x is the mean of x, regardless of whatever distribution the x is, right? So this is the population mean, And sigma x is the standard deviation of x, is the standard deviation, a population standard deviation. So if you draw a random sample of size n, and when this n approaches to infinity or increases and approach to the whole population, the random variable x bar, which consists of sample means, tends to be normally distributed. So what does that mean? So whenever we draw samples, the size, whenever we draw the sample, the sample mean itself is random, right? So we talked about it a little bit before, that sample mean, even if the population mean is a constant, population mean is a constant out there, except for we just don't know it, right? So the sample mean x is random. Why? Because the way we're sampling is random, and it has to be somewhere random to make sure it's not biased, right? So the sample mean itself is a random variable. And basically we're saying that if we make the sample big enough, then this sample mean, this random variable, the mean itself, not the x, okay, the x itself can be any kind of distribution, but the sample mean is going to be normally distributed. That makes sense? So that is a very useful theorem, because now if all we are caring about is the sample mean. For example, if we want to know the population mean, mu x, then as long as we are going to draw a big enough sample, then we can assume this sample mean is normally distributed with the mean of the population mean. So we can take the sample mean x bar. Remember, that itself is a random, right? So we can take its mean, and equate that to the population mean, which is essentially what we want to know, right? So we don't need to actually study the whole population. We can just take a big enough sample, calculate that sample mean, and then that will get to the mu x. So what is the sample means? What is the sample means standard deviation? Well, that will be the sample deviation, which is the population standard deviation divided by square root of n. Excuse me. So here's some more verbal explanation. I know this is somewhat deep to comprehend, but imagine this. Once we have this central limit theorem, we can use it to estimate the mean of any kind of population distribution. We don't even care what is the population distribution mean, and it becomes the fundamental, the foundation of a modern regression and many other models. So the central limit theorem for sample mean says that if you keep drawing larger and larger samples, such as rolling 1, 2, 3, 4, 5, and then 10 dices, and then calculating their means, okay, you keep drawing larger and larger samples and keep calculating their means, the sample means from their own normal distribution, right? The normal distribution has the same mean as the original distribution of the population distribution, and variance equal to the original variance divided by the sample size square root. Right, the variable n is the number of values that are averaged together, not the number of times the experiment. The number of values that are averaged together, not the number of times the experiment is done. So that is basically the sample size of your last experiment. So formally, we can say if you draw a random sample of size n, the distribution of random variables x bar, which consists of sample means, is called sampling distribution of the mean. A sampling distribution of the mean approaches a normal distribution as n, the sample size, increases. So this is exactly why when we are reading any kind of study, we need to pay attention to the sample size. We want to make sure that sample size is big enough so that the mean is normally distributed with the sampling distribution of the mean centered at the population mean. And that's how we make sure that those studies, when they draw a sample, whatever conclusion they get from the sample is unbiased. Right, the standard deviation of the mean. So since this random variable x bar, that sample mean, it has its own it has its own mean and it has its own standard deviation. So we can calculate its own z-score. So the z-score that's associated with it is equal to the whatever sample average value of the x mean, x bar in that one sample minus the population mean divided by its standard deviation, or we call it the standard error of the mean. Quick example, unknown distribution has a mean of 90, standard deviation 15. The samples of n equal to 25 are drawn randomly from the population. Found probability of sample mean is between 85 and 92. So first of all, let's calculate what is the mu x, right? So the sample mean x bar should have a normal distribution. It's normally distributed with mu x and the sigma x divided by square root of n, which is equal to mu x is 90, right? Sigma x is standard deviation of 15, and n is 25, so square root of 25, which is equal to 5. So its mean is 90, and the standard deviation is 3. Okay, and now we can draw a graph and say, oh, this is the mean at 90, right? And this is 92, this is 85. So we can calculate the z-score. The z-score of 85 is equal to 85 minus 90 divided by 3 is equal to 5 over 3, or equal to 1.6667, right? Negative, sorry, negative. And Z92 is equal to 92 minus 90 divided by 3 is equal to positive 0.6667. And if we take a look at the tables, we'll be able to find the z-score, the probability of the z-score. Just one moment. All right, so negative 1.66, 1.6, so negative 1.66, this one, the 1.67, so somewhere between 0.485 and 0.475. So it's approximated equal to 0.480. And then this one is equal to the one with positive 0.667. So somewhere between here, 0.7454, 7486. So somewhere in between, let's say 3 in between 1.5, 1.5, 1.6, 7470, say, approximately. Oh boy, 7470. right? So the probability the sample mean is between these is basically the difference between these two numbers. Oh, sorry, I missed 1 0 here. So if we come back and take a look at this table for the negative 1.667, so there is 0.04, not 0.4. So my mistake. It's 0.048, which is an estimate, and this is 0.747. So my estimate, that is the probability. So Z85 was the 0.048 was this little part, and the Z92 that I calculated was this part, the cumulative probability of X being the standardized normal or the z-score being less than 0.667. So we get the probability of Z92, Z is less than 92, is equal to 0.747. This one, probability of Z is less than 85 is equal to 0.047. So then the probability of the Z, the mean between these two numbers, 92, is equal to 0.747 minus 0.048. It's not as precise as what the calculator was giving out here, but it's very close. It's equal to 0.747 minus 0.048, 0.6990. 0.6990. So have you got it? And again, the book has explains how you can calculate it using TI calculator. I still prefer that you learn how to do it in the table, because you can bring that to the exam. You can use that anytime without the calculator. Okay. So in the calculator, if you find a normal CDF, the normal cumulative distribution function, then you can take the lower value, higher value, the mean of it, the standard deviation of it, and you put it in there. It will tell you the answer very quickly. Okay. Another example, in a recent study reported in on the Florida blog, the mean age of table user is 34 years. Suppose the standard deviation is 15 years, take a sample of size 100. What are the mean and standard deviation for the sample mean ages of the tablet users? All right, so the sample mean ages will be getting at least very, very close. If the sample size is big enough, it will be very, very close to the mean age we're talking about here. So that mu x is equal to this mu here, that 34, right? So the standard deviation, that's the mean. The standard deviation is equal to the standard deviation 15 years divided by square root of 100, which is 1.5 years. So what does the distribution look like? It will be a normal distribution. The central limit theorem always says that whatever your result is, that mean the sample mean age will become a normal distribution. Right, so find the probability of sample mean age is more than 30 years. So the probability of X bar is greater than 30 years is actually equal to the 1 minus the probability of X bar less than 30 years. And this is usually the less than is the cumulative distribution function that we talked about earlier. So it becomes 1 minus the probability of the z-score of it is less than 30 minus 34 divided by 1.5. Right, same probability is equal to the probability of z-score is less than minus divided by 1.5 is equal to negative 2.6667. Right, so coming back to the table, negative 2.6. Hope you can see it. All right, so negative 2.6667. So it's somewhere between 0.0039 and 0.0038. Let's say 0.00385. Just an estimate. 1 minus 0.00385. Notice that even if these critical values are negative, the final probability has to be positive, right? So we can get 0.99615 or 62, 0.9962. So that is for question C. Question D, find the 95th percentile for the sample mean age to 1 decimal place, right? So D basically is saying that there is this critical value, let's call it XC. Right? So this critical value is there so that the probability of this X mean, X bar, less than XC is equal to 95% or 0.95. So we can think about as the z-score, the probability of z-score is less than the XC minus X bar C minus X bar divided by this 1.5. This is 34 is equal to 95%. Right, so what is that C? Well, coming back, what is the 95%? Let's see, where is 95% goes on 95 to 95 here, between this one and this one, between 1.6 and 1.64 and 1.65. So let's call it 1.645. Right, so that Z, that critical value, XC minus 34 divided by 1.5 is equal to 1.645. Right, so that XC should be equal to 34 plus 1.5 multiplied by 1.645, which is equal to plus 34, 36.46, 36.5. Okay. Have you got it?